Shown in the figure below is a series of blocks and pulleys. The 3 kilogram block will slide across the surface and experience an acceleration A. Although this is clearly a force problem, there is one complexity to this force problem, and that complexity involves the 8 kilogram mass. The 8 kilogram mass is suspended from a compound pulley. What this means is that the string connecting the 8 kilogram mass and the 3 kilogram mass is not attached to each one, but it is simply attached to the 3 kilogram mass and attached to the ceiling running over a pulley above the 8 kilogram mass. Because of this, the distances that the 3 and 8 kilogram masses move are not the same, nor are their velocities, nor are their accelerations. So rather than summing each set of forces and setting them equal to ma, the one and only acceleration in the problem, we're going to have to decide whether these forces will sum to a subscript 3, which we'll consider to be the acceleration of the 3 kilogram mass, or a subscript 8, which will be the acceleration of the 8 kilogram mass. These are not equal to each other, but are related in a simple way. Let's imagine for a moment that the 8 kilogram mass falls and moves downward by a distance that we'll call d. As indicated in the figure, there is more string above the mass on the left-hand side and also on the right-hand side. So the total amount of extra string over by the 8 kilogram mass is twice d, accounting for these two pieces. If we ask ourselves where this string has come from, the answer is that it must have come from the 3 kilogram mass. This means that when the 8 kilogram mass moves by a distance d, the 3 kilogram mass must move by a distance twice d in order to have supplied that much string. Therefore, the 3 kilogram mass will always be moving twice the distance of the 8 kilogram mass. It will therefore at any moment have twice the velocity, and it will also have twice the acceleration, so that A3 is twice A subscript 8. When we formulate our free body diagrams and we write our equations, the one thing we'll have to be careful of when dealing with a compound pulley is to sum one equation to A3, the other equation to A8, and use this relationship to assist in solving for the rest of the variables. The first step in every force problem is to draw a free body diagram, and I'll begin with the 8 kilogram mass. This dot will represent the 8 kilogram mass, and we list every force acting on the 8 kilogram mass. The first force is gravity, which is of a strength m times g, where the mass is 8. Secondly, we need to account for the tension. The string is not attached directly to the 8 kilogram mass, but strings always pull. Examining the diagram carefully, we will see that there is one portion of the string to the left-hand side of the pulley, and a second portion of the string to the right-hand side of the pulley. Each one of these pieces of string pulls and applies a tension of an amount T. Therefore, completing our free body diagram requires that we draw the tension T twice in the free body diagram, once for each half of the string. The principle by which we align the coordinate system is the same as always. We do so with the acceleration, and we recognize that the 8 kilogram object will accelerate downwards, so we'll call plus the down direction. Analyzing the y dimension for the 8 kilogram object, we see that 8g is in the plus direction. We have two tensions pulling in the minus direction for twice t, and the sum of these forces is equal to 8 times acceleration subscript 8. We'll put a box around this equation and save it for later. The second part of the analysis involves analyzing the 3 kilogram mass. Again, the first step in every force problem is to draw a free body diagram. This dot will represent the 3 kilogram mass, and we'll name each and every force acting on this mass. First is gravity, which is 3g downward. Next, the 3 kilogram mass lies on a surface. All surfaces will apply a contact force which will at least have a normal force as one component and may have friction. In our case, there is friction. Since the object slides to the right, the friction will be to the left and will be of an amount mu k times n. Finally, the 3 kilogram object is in fact attached to a cord, and so there will be a tension going to the right. We always align our coordinate system with the acceleration. Since the 3 kilogram mass will be accelerating to the right, we will select that as the plus direction, and the other coordinate will be perpendicular to this, up and down. We'll analyze the vertical coordinate first, so that in the y direction, the normal force we'll call positive, minus 3g, equals the acceleration in the y direction, which is 0, leading us to the result that n is 3g, which is equal to 29.4 newtons. Although we weren't asked for that originally, since this problem yields one two-dimensional free body diagram and one one-dimensional free body diagram, clearly there are three unknowns, and this is one of the three unknowns. More to the point of this problem is an analysis of the x direction. The positive x direction is along with the tension to the right, and we have one force in the negative x direction, which is mu k, times the normal force. Finally, the sum of the forces is m times a. The mass of this object is 3, and the acceleration is what we have called a with a subscript 3 for the acceleration of object 3. When we bring these three equations together, we see we have three equations in three unknowns: tension, A3, and A8. Although, because of the compound pulley, the algebra will be slightly more difficult, it's not that much more difficult than a typical problem. The first thing we're going to do is we're going to eliminate the variable A8, because the problem itself asks us to solve for the acceleration of the 3 kilogram mass known as A3. We see that A8 is half of A3, and we'll substitute that result into the second of our two equations, yielding us the following pair. Here, 4 times A3 is the substitute for 8 times A8. We now have two equations in two unknowns, and although the tensions have followed the usual principle that each tension should appear once with a plus sign and once with a minus sign, we see that we have twice t in the black equation and 1 times t in the green equation. The easiest way to place these in the familiar context that we're used to is to double the first equation by multiplying the entire equation on both sides of the equal side by 2. This will yield twice t in both equations, making them easy to solve. After we've completed that algebra, we have the following pair of equations. These two equations are now easy to solve simply by adding them together, causing the tensions to cancel, yielding the result (8g minus twice 0.2 times 29.4) is 10a3. This can easily be solved to yield the answer A3 is 6.66 meter per second squared. Call it an evil problem if you like. What we need to do with that result is plug it into either equation. The second one seems simpler, in order to solve for the tension. Tension is 8g minus 4 times the acceleration divided by 2, which in newtons is 25.9 newtons.